What's up, YouTube? I'm Leo with Remodeling Calculator. We're inside of my camper. What we have here is a completely off-grid 48-volt system with two Growatt split-phase inverters that output 110 or 240 volts. And we have this Fujitsu ductless mini split heat pump. Okay, so this is a 33 SEER air conditioner, but it is also a 22,000 BTU heating unit, and it will work in -15 Fahrenheit, probably even below. And it is completely powered by this system here, the 48-volt batteries and the two split-phase inverters. And I have this breaker panel over here that will supply the power to this unit, and we can also wire some additional outlets from it. But the sole purpose of this is to power the heat pump. Okay, we're going to add some solar panels in the future to charge the batteries. Right now, to charge the batteries, I have to switch the main inverter into a single phase. However, in a split phase, it works fine, and I'll show you right now. Okay, so it is pretty cold in here, like I said, and we're going to measure the temperature of the wall. This 34 degrees. We have this super accurate HVAC thermometer for installing the heat pumps and other HVAC equipment, and the thermal probe is just hanging down here. When I have, as I bring it closer to you, the temperature rises, but it was 35 degrees. Okay, and we're going to use it to measure the heat output from this unit. Now it shows 35 degrees again. And I have this like regular IKEA thermometer that has acclimated and shows 36 degrees. So let's turn this thing on and see how it works. The first thing we need to turn it on is switch on our batteries, then our circuit breaker right here, and our inverters. And so it is right now, the battery voltage is 53 amps, 53 volts, and this is set up as the host inverter, and this is a 2P inverter. Okay, so the main split phase inverter and the secondary split phase inverter. Each one provides 110 volts via this 10 gauge cable that goes into the main panel. And so one leg of each of this cable, the black wire, goes into this 30 amp breaker right there. And this is our main on and off breaker. Okay, and the second leg from the second inverter goes into the other part of the breaker. Our ground and our neutral wires are spliced in a ground and neutral bus bar over there. So let's switch our main breaker on, and let's switch our heat pump breaker on. So let's turn on our heat pump. So the time right now is 8:05. We have it set on 82 degrees and the fan on high. So what's going to happen now, the compressor is going to warm up, compress some refrigerant, bring up its temperature, and then it's going to push the hot refrigerant through this indoor unit, through this coil over here. So this is an evap coil, but in the heating mode it becomes a condenser, and then the outdoor becomes an evaporator coil. Let's measure our temperature now inside there. This shows 34 degrees, 35 now, 37 because I'm holding my finger next to it. While it's warming up. So these two Growatts, each one can push out 3000 watts of power in a single phase, 120 volts. And when in a split phase, they together push out 6000 watts. But again, that's limited to 3000 on each leg. Okay, and each one of these inverters supports up to 4500 watts of solar. And we're going to put about 2000 watts of solar on the roof of this camp. So over here, we have two 24-volt batteries that are put in series to make it a 48-volt system. Okay, you'll ask, like, why is this wire so thin? It's a 4 gauge. I know it's a little bit thin. When I built it, it was for a single inverter, and while I'm waiting on USB 175 connectors, I'm going to leave it because I'm not going to draw more power than this wire can support. This here is not bare copper wire, okay? It's insulated copper wire, 2 gauge. It is clear insulation, that's why you can see the actual copper. I got the 2 gauge wire from AutoZone, and these two inverters are put together via these two communication cables. Now each cable has a male and female plug, so you will not get it wrong. Just plug them in, but just so you know, one cable is plugged on the left side over here, and the other end of that cable is plugged on the right side over there, and so they're closest to each other. And the second cable, they're the furthest away from each other plugs. So this one goes to over here. But again, you cannot mess it up because they're male and female only, and each of these plugs is either male or female. One more thing, when you program this, the program setting that you need to use is number 23. However, when the inverter is on, you cannot enter setting number 23. So what you do, you go into settings by holding the enter button, you scroll down to 22, and then you switch off the inverter. So while you're doing that, this inverter should be off completely. Okay, you switch off the inverter, the screen will stay on for another 60 seconds or so, so you have enough time to scroll down to 23, which then becomes available, and you set this to the setting 2P0, okay? And then you do the same, then it will shut off, you will turn it back on, and it will work properly. You do the same thing on the second inverter here, and you set it up to setting 23 to 2P2, okay? And then you do not have to set the degrees of the split phase from 120 to 180, because that will automatically set both inverters to work in a split phase of 120 and 240 volts. That's it. That's the only setting you need to make. All right, our heat pump has warmed up, and we are reading 97 degrees. It's gonna get warmer. And this will go up to as high as 160 degrees inside that coil. It's gonna be really toasty in here. So again, guys, we have heat in this camper. It is completely off grid. While it's parked in my front yard driveway, it's completely off grid. It's unplugged from 240 volts. This system here is completely contained. And once you add solar to it, you can charge these batteries during the day, and during the night you can heat it. In a cooling mode, this unit consumes on average 500 to 700 watts, depending on the space that you're trying to cool. I have a 600 square foot space, so then it goes to maybe 900 watts of power in a cooling mode, but it's super powerful. In the heating, once everything settles down, it will run at about 1500 watts. If we close this door, it will run probably at like 900 watts, because this is a small space. It's 100 square feet here in this bedroom. 900 watts is about half of how much a 1500 watt space heater consumes. And that thing will never heat this room in the winter cold. This will do it in 5 minutes. So now let's take a look at our power consumption. So right now it is pulling about 10 amps, and that makes it about 2400 watts of power that it's pulling. But give it 15-20 minutes, it will drop to below 8, and then after half an hour to an hour it will drop to about 5 watts per leg, and that will be like 1200 watts, and then we'll keep dropping because this is a pretty small space. So here I changed the fan speed to auto and leave for a couple of hours. Before I do that, I'm trying to make sure that you can see both the temperature at the exhaust fan of the indoor unit and also the amperage. However, my clamp meter will only stay on for about 5 minutes. But you can see that the power draw begins to drop as the unit reaches set temperature and kind of goes dormant at about 0.35 amps. In the automatic mode, these inverter compressors are very efficient and only run when they need to reach a set temperature, therefore saving you a lot of energy. As you can see, the top temperature at the exhaust reached about 130 degrees. Your sensor detects that room temperature has dropped below a certain threshold. It will turn on the compressor again until the set temperature is reached. After I left the room, the heat pump has run for about an hour and a half. After that, the battery cut out because of the low voltage disconnect, and the whole 240 volt system went down. Basically, one of the inverters shut down and there was no more 240 volt power, so the main inverter went into a fault mode. When I left the room, battery voltage was about 50 volts, and here you can see voltage dropping to about 47 volts, and in a few seconds it will cut out and the second inverter will go offline completely, which will result in a fault light on the main inverter. Alright, so time is now 2:26. I've been away for a couple hours. Temperature reading over here is 59 degrees. What we have is a fault light over here, and this inverter shut down. The temperature inside the cabin was 68 just now it's 66. It's kind of warm-ish. So the battery shows 51.3 volts. Okay, so we turned on the second inverter and the power, this fault went away. So they're now connected. Something clicked. This thing is closing. And it ate my temperature probe. I wonder what happened. Probably a low battery disconnect. This one shut down, that one didn't. Oh, it's actually turning on. Again, I didn't touch it, the remote is over there. But it's an interesting test. So the system ran for almost 2 hours. It's blowing somewhat warm air. You can see a little fluctuation on the temperature over there. Went to 71. Now it's 63. The blower motor is spinning. The remote is over there. So it's set to, I think it's 78 auto. Okay, now the 82 auto. So I changed the fan from high to auto, so it would modulate depending on the set temperature. Okay, so the compressor is coming back online. It's now pulling 2.25 amps, 2.5 amps soon, and it's warming up. Over here we already have 74 degrees. You probably caught it on the camera. The louvers went down a little bit, so now it's blowing warm air again. And you can see this on the temperature gauge over here. Move this closer so you can see. Now keep in mind, I left that door open. It would be more realistic heating scenario where it would heat the rest of the cabin. Now if it was just 2 people, you probably want to close this door, keep just the bedroom warm. We have 100 degrees air coming out, and we're using close to 6 amps right now. And our batteries are slowly approaching, so they just dropped below 50 volts. I think we should set it for 46 cutoff, because when you pull the energy out and then you shut it off, the battery voltage reading actually comes back up. So when there is no load, the voltage is higher than when you pull the power out of the batteries. Then the voltage reading drops. Okay, we have 47 volts, so that's what it is. Yeah, so they cut out because we have 47 volts. Ah, one of the batteries cut out. Look, I have 23 volts over there. So the BMS and one of the batteries cut out, and now they're both shut. That's what it is. The BMS has shut down. So it was a pretty nice test. I've learned personally a lot from it myself. So basically, to recap, I left the system running for a couple of hours, and I left the heat pump running, okay? And what happened, I don't know how well the batteries were charged. They were showing 53 volts when I started the test, so that's kind of low. And I put them back on the charger right now. So during these 2 hours, at some point, and I'll have to review the video, I put a time-lapse recording while I left, one of the inverters cut out, and the second one was showing fault. And that happened relatively toward the end of the 2 hours, because when I came, this temperature sensor that was still inside the unit, it was showing 70 some degrees. Okay, so it just shut down and it started to cool off right before I came at some point. And the temperature over here, I had this thermometer over there, was 66 degrees. So the space was kind of warm. Again, I'm not sure why one of the inverters cut out during the test, and I'll review the video, but later I powered them both down, restarted them, they came on, this was working for about 5 minutes, and then what happened, the BMS on one of the batteries cut out, and so it was showing only 23 volts on both inverters. They both went into fault and shut down. Number one, we definitely need a bigger battery bank. So this is about 5 kilowatt hours. I think nominal 5.2, but again, they weren't fully charged. You know, you don't pull the full capacity out of lithium iron phosphate batteries. It's better to cycle them like 60 to 80%. Otherwise, you shorten their life cycle or lifespan. At this point, I'm leaning toward getting 4 of these batteries. So this is a battery Evo 12 volt battery. So this is a pretty massive battery. It's big in size, and the cells inside of it are big. So this particular battery, most of their batteries are new cells. This one is refurbished or reconditioned cells, and they're guaranteed to pull at least 150 amp hours, these batteries. Now, from looking at tests of other people, they've gotten close to 160 amp hours. But anyway, this battery is pretty inexpensive. It's a 2 kilowatt hour battery, costing $600. Has a BMS, low temperature cutoff, SBF175 connector, this circuit breaker and switch right here, battery monitor. It's a little bit big for your typical like camper battery drop-in replacement, but other than that, if we put 4 of them together, that's 8 kilowatt hours. That would bring my system to 13. I can actually fit 4 of them right in here. So for $2,400, you get 8 kilowatt hours, okay? Actually, it's a little less than that, because if you use my promo code RemodelCalc, you get 7% discount, maybe more. If you watch this video in the future, the discount may have increased, but at this point it's 7%, free shipping. And those batteries right there on the bottom, they're battery, big battery. These are no longer sold, no longer produced. And so right now, Big Battery basically just buys Battery Evo stuff, puts their label on it, and calls it Big Battery. A video from Average Joe channel, and he takes apart a Big Battery Husky, and you can clearly see a Battery Evo logo on that PCB bus bar. I'm not sure if Battery Evo builds all of Big Battery's units, or some, or none, but they sure look very similar. If you look at their websites, all the products look very, very similar. And actually, even a couple years ago when I bought my Big Battery units, the black ones in my video on the bottom, Tech Direct Club and Battery Evo basically sold identical units on their websites. And it's as if like the same company manufactures them and then sells them to multiple online retailers. However, inside of them, you see Battery Evo logo. So my guess is that Battery Evo builds them, and then other people rebrand them, private label, and so on. Okay, but if you watch videos of other people, they open them up and they see a Battery Evo BMS, Battery Evo PCB bus bars. The cells are not marked and are not shown usually, but essentially from Big Battery you're buying a Battery Evo for about 10 to 15% markup, maybe even 20 in some cases, and then you pay for shipping. Unless you order 4 units, you pay shipping. And shipping on these batteries could be like $300-400 easily. At some point, it's probably cheaper to just get another battery than pay shipping. So with Battery Evo, you don't pay shipping. It's free shipping in the lower 48 states. And your cost out of the gate is 10 to 15% less, plus another 7% you save with my promo code. Anyway, so my thinking is to buy 4 of these and put them over there on the bottom. So pull out 2 drawers, maybe leave them there as a fake, like just to look nice. Because at this point, it's too much weight right over here. I don't like it. But if we put them on the floor and fix them in place, you know, we don't have too much weight here. It's on the bottom, and we have like a 13 kilowatt hour bank. If you have fully charged batteries, I think this heat pump can actually run you all night. And then in the morning, basically recharge it with solar. Now we need to figure out how to charge it on shore power. And so maybe my choice of a 240 volt heat pump wasn't a great choice for this particular application, because we're in the camper and I actually don't know a single campground that has 240 volt connection. So for example, Mr. Cool, they have a 12,000 BTU heat pump that works on 110 volts. Now it's not as efficient as this one. The reason I put this heat pump in here, this is the most efficient heat pump, single zone heat pump that you can buy in the United States. It's 33 SEER, has 22,000 BTUs of heating capacity, and it's 14 HSPF, which is a seasonal heating coefficient. I'm not going to decipher that HSPF right now, but it is, mamash, the most efficient single zone heat pump that you can find. Even the Mitsubishi doesn't come close. Theirs is like 32 SEER. It has a much smaller heating capacity. So that's why I put this unit here. And originally it was actually plugged into shore power. We put pipes on the ground. We ran 240 volt service, 30 amps. And so it was plugged into the shore power, and it was stationary, and the person lived in this camper. So my goal originally was to actually create this setup here. You know, 2 inverters in split phase, solar panels, which I'm going to do soon, lithium batteries, and have on the go really powerful heat pump that's super efficient, a really nice solar lithium off-grid system. Okay, now to charge this with a shore power is a problem, and you won't always have sunny days. You won't always have 2 kilowatts of solar panels on the roof. You know, not every camper is capable of that. So I think for most people it actually makes sense to use a 120 volt unit such as Mr. Cool DIY, or even not a DIY. Like, I actually show you how to install this unit. All the videos are available on the channel. I'll link them in the description. With a little bit of learning, you can actually install a more efficient system and do all the line set and all the refrigerant, pull the vacuum. Mr. Cool, just with Mr. Cool DIY, you just avoid all that because the line sets are pre-charged with the refrigerant, and if they're quick connect, you don't have to pull vacuum, you don't have to deal with any of that stuff. However, for myself, since I'm an HVAC technician, I have all the tools, it's much easier to do a more efficient system than Mr. Cool, because Mr. Cool in many cases is not flexible enough. Like, the line set is 25 feet or 15 feet. What if you need a longer run or a shorter run? What do you do with the extra? You know, if you start coiling it up, so you create an oil loop, oil trap, and that is bad. Like, a lot of people, you can see a lot of people do that. If you see a person that coils up their line set, stop watching it. That person is an idiot. Stop watching his videos and just leave, because you cannot create an oil trap on the refrigeration lines. It's very bad for the compressor. It will cause to a system failure in the future. Anyway, as a recap, we need a bigger battery bank, and I'm thinking about putting 4 of these guys on the floor. We'll have 13 kilowatt system, maybe put a couple more batteries over there, expand it even further, make it like a close to 20 kilowatt hours, and that's huge. But then with 20 kilowatt hours, you can run this heat pump for a very long time. It's better to keep it on a short power if available. Therefore, it's better to use a 110 volt system. So 120 volt heat pumps, I really don't like their specs. They're really underpowered. So Fujitsu, they have great systems, except for their 120 volt systems. They are so inefficient. They're only 15 SEER, their heating capability is abysmal. It's just like an air conditioner for a small office on a budget, you know, that you don't have to wire. You can just basically plug it in the wall because you have 20 amp service. I will actually do a technical analysis on the Mr. Cool and some other systems. Now, Pioneer, I'm very skeptical about Pioneer. I think Cooper & Hunter is a much better product because it's actually made by, I think it's Miata or something like that, one of the biggest heat pump manufacturers. Now it's a Chinese company, Chinese engineering. Fujitsu is head and shoulders above and ahead of them in the quality, in the efficiency, in the engineering, in the longevity. But still, Cooper & Hunter is a rebranded Miata or whatever the company is called. They're a pretty big company, so their equipment is more tested, and you know, they have more feedback how to make it better. I will research the technical capabilities of those 120 volt systems, and maybe I'll pick out a good one, and maybe I will switch this out and make it more usable. So like if I come to a campground, I can actually charge all my batteries, because again, charging these batteries right now is such a pain. I have to disconnect one of the inverters, I have to shut it off. You can see it's off. I have to put this back in a single phase, and only then I can plug it in. So here's my plug, and it's charging. This is 110 volts. So if I want to charge the batteries with both of these inverters in split phase at the same time, I have to bring in 240 volts with a neutral, because there is a neutral connector on there. And the diagram from Growatt shows that you need to bring a neutral. So probably better to keep it at 110 volts. But this is what I have. This is what I'm going to live with for now. And it's working great. We just need to expand our battery bank, put as much solar as possible on the roof of this camper. And so for that, my plan is, this camper is 32 feet long, okay? So up in the front, we have a satellite antenna. I don't want to touch it. We have a regular antenna that just like lifts up. I probably want to keep that as well, although there's very little use for it nowadays. There's a little TV over the air. But I have 2 air conditioners in the center of the roof. They're completely useless. They're so power hungry. And with this thing, I don't really need them, because as I drive, I could have this running of the batteries and of the solar. And if anything, I could even plug in, like attach a 120 volt charger. Although as I drive, where do I get that power? Probably from the alternator, so that complicates the system. I need to DC to DC charger for the camper batteries. But it's all solvable. We can solve that problem. Anyway, we can like run this as I drive. For example, in Florida, I had to run my roof air conditioners to keep the cabin cool, because like my kids were sweating, and the engine AC wasn't able to keep up with the rest of the camper because it was just so hot outside. It was August in Florida. It was super hot. So I had to run rooftop ACs. So instead I could be running this unit. It would cool the cabin, and at the same time it would be charging from the solar panels if there is sun. If there is no sun, it's probably not as hot, and the engine AC can keep up with the camper. And that's where a bigger battery bank comes in handy. So another thing, the weight of the lithium batteries. Now they're much lighter than lead acid. However, they're still heavy. Like this big boy over there weighs like 60 something pounds. So if I put 4 of them, that's 240 pounds. That's a lot of weight. But I have an on generator right over there. And I don't need it. I don't want it. I used it maybe twice. Actually, I used it as I was driving. I was running my generator to run my ACs over there to keep the camper cool. That was so ridiculous. Yeah, so I can take that out, sell it to somebody. I can probably get like a couple grand for it. Those things are expensive. I'll just sell it. That will remove a lot of weight. That thing weighs probably 300-400 pounds. So by removing that, that opens up a whole base. I can actually store stuff over there, and it will decrease the weight on this side of the camper, and then I will be able to put more batteries over here. I also throw out this TV. That's another like 50-60 pounds. So remove the extra weight that we don't need here. Don't overload it. And then I can have a really nice battery bank with solar panels. So I removed the 2 ACs, propane powered fridge right over there. And this way I don't need the vent for it on a roof. So I can remove the roof vent and put a 110 volt AC in there and run it off an inverter. I gotta wire another inverter into the system. I need to think the whole, like how to kind of make the whole camper work together, the whole power system work together. So that's a whole different story. And yeah, so this basically clears most of my roof all the way to the front where the satellite antenna is. And I should probably get rid of that like crank up antenna over the air. And then I have about 28 feet of clear space on the roof to install solar panels. And then I can fit like 8 370 watt panels. Wow, that's like close to 3,000 watts. That would be a massive solar array on the top, on the roof of a camper. Wow, that's insane. So that's the plan. That's the plan. We're going to do that. In the meantime, I just need to make a decision if I should get this battery EVOS 150 amps or something else, because they have smaller batteries that weigh less and are more dense, the newer ones. But anyway, those are not as inexpensive. So with my discount, you can actually buy this for like $560, give or take, for 2 kilowatts. I think it's a pretty good deal. Now it's 12 volts, so to get 48 volts, I would need 4 of them. But then because there are so many batteries, I don't need such a thick cable going to each battery bank, because now they're all pulling together, so there's less amperage going from each battery bank. And now we have 2 gauge wires over here. That's plenty. That's more than enough, more than we need. So we're going to keep that. Probably upgrade this to this is a 4 gauge and that's a 2 gauge. We may even keep it for now once we add a second battery bank. So yeah, that's the plan. Alright guys, this was a long explanation of what is going on, what I want to do. But it's a great proof of concept. So again, I'll show you exactly how to put all this together. And my final thinking is probably better to stick with 120 volts. This way you can charge your system from at any campground. So if you have 30 amps or 50 amp service, just connect to that, charge it. You can even have like a 30 amp wire going from here into the shore power at the campground. You can have 2 of them, and so you'll have 2 inverters charging the battery bank at the same time. One at say 20 amps, one at 30 amps. That's 50 amps. That's a lot of power. And overnight you can recharge the whole battery bank even without sun. And many campgrounds you can actually stay there for like 20 bucks. Not a bad deal. Usually state parks and stuff like that, not private. But yeah, great proof of concept. I really like how it's working. Learn a lot of new things from actually running this. So thanks for watching guys. Again, I'm Leo with Remodeling Calculator. I will link all the steps of this installation in the description below. I will also link all the steps of the heat pump installation. I'll put a link to the battery Evo page and also put my discount code in there, as well as all the tools that you need for this. These inverters, I got one of them from Watts 24/7 and one of them from the other website, solarsomething.us. Link it in the description below. They were about the same price. They work great together. So yeah, guys, thanks for watching. This is Leo again with a completely off-grid 48 volt double Growatt inverter and split phase and a ductless heat pump. See ya.